Hello, everyone. Yes, I will bring you to a completely different modality from language to tables. Some might think, well, isn't that the same? But I don't think we talk tables to each other, but natural language. So clearly there's a big difference. And I completely agree with the final takeout here that data scientists, might get a lot of support if you adapt language models or table representation learning models towards data science pipelines as well. And I look forward to that moment to come. So my talk will about table representation learning. My name is Madelon Hulsebos. I'm a PhD candidate at the University of Amsterdam, particularly working in the Intelligent Data Engineering Lab. So I think, pressing twice as told. So I think we've by now all seen the impressive capabilities of representation learning and transformers in general over images, text, and also code, right? For very fun tasks like explaining jokes, completing code, which is extremely useful. But what about tables? And I really like being here and giving this talk here because there's like 65%, I think, of industry experts. So I'm really curious to see who's actually working with images, whose databases are filled with images from the industry experts here. Some hands, great. So whose databases are full with tables? All right, that's fantastic. So I think it's like half here. I think, and I'll show some very interesting stats perhaps to you later on. So if you consider the database management systems around, it's actually relational database management systems who are most popular as indexed by DB engines. So it's not actually that we're working in organizations like governments, for example, or some other big companies with large amounts of documents or images. No, we actually gather so much data in tables and we store them in relational databases. So there's huge potential with regards to data availability. But also if you look into the data modalities that you can find in the wild, so for example, on the web, it's actually tables as stored in CSV files, which dominate these numbers, as for example, indexed by Google dataset search. So I think, and of course, you might find some text in these tables, and you might also think the other way around, as Neil suggested, I think, to retrieve different documents and then aggregate numbers from those documents to get to an answer. Or you could consult your huge databases with tables and try to find answers from that. And I think there's a huge interesting intersection there. But as we've just discussed about, I think, data scientists and what they do, I think 5 years ago, the popular job was data scientist. I was myself one as well. Now I think it's prompt engineering, but there are so many use cases actually that leverage data science and typically operating over tables. And if you consider a typical pipeline here, so this goes all the way from, extraction of data to integration of data to, querying and query optimization, but also to more on the analytics end, data augmentation, data transformations, data preparation, and then you can, make all kinds of visualizations, maybe some full machine learning pipelines with that. And all these tasks here, they actually operate over tables. I think we all know scikit-learn. They are really tailored towards tables. So I think there's huge potential if we try to adapt these transformers to work with tables as well, to not let them sit them idle in these databases. But beyond the wide data availability, the application potential, there's also huge interesting aspects about tables that make it suitable, but also challenging for transformers to work with. So for example, tables, they might come in a singular table or with many relations with other tables. How do you deal with that? Do you just dump them into ChatGPT and hope for the best? That's just, dubious whether that will work. But they also can come with so much context, so much metadata that you can actually leverage to automate many of those tasks that we just saw. But I think what might actually be more challenging and that everyone tries to ignore a little bit is that most of the tables actually don't really incorporate so much text. So most of these tables that we find in databases are full of numbers. And yeah, how do we deal with that? So that's a huge challenge that is still extremely open, and I invite you all to think along about it. So I'm here to motivate that we should instead, well, expand our focus from traditional modalities like images and text, and also leverage the huge capabilities of transformers for tables. So I'll give you first a brief survey of what kind of adaptations has been made so far and the advances here before we move on to the interesting challenges and developments. So on a very high level, you have a table, perhaps you have a question, you put that through one of the models that you find out there, and then you can either use the embeddings for some tasks that you're interested in, or fine-tune this model towards a task. So for example, fact verification over tables or question answering. Okay, so let's take this step by step. So for example, on the input side, what is typically done is you have a table and you simply serialize it. So you have a table and you make like a sentence out of it. That's just the current state of the art that we're at. And then you tokenize it. So here's a brief image of how this is typically done. So pretty straightforward. You just take the header, for example, you concatenate all column names and then add all the rows. Then you have your like flattened table, and then you hope for the best. There are actually many variations to this, but I leave that for you to discover yourself. We did an interesting survey on this if you want to find out more. But I want to move on to the actual model side. So of course, we know the attention mechanism, and this has been actually adapted towards capturing the structure of tables. I gave you two interesting variations here. So first is vertical attention, where instead of just looking at a sentence or the entire document, these models can actually learn relationships across a single column, so that your cell kind of restricts its attention towards only values from that certain column. A bit wider, because we don't only have columns, of course, to take into it as context, but also rows. So there is this extension towards a visibility matrix where cell values can also attend to neighboring cell values in the same row and not beyond that. So that's like the adaptations with respect to the attention mechanism. And of course, there are very specific pre-training tasks that sometimes might be similar as we see for language, but can also be very specific to tables. So an example is recovering column names or recovering cell values. What I think is more interesting is introduced by TAPEX, and that's actually synthesizing SQL queries and then executing them on a table and use the output as your label to learn the semantics then from your serialized table along with this query. And I think that they also show that this is way more efficient way of pre-training to capture the semantics of these tables. Then on to the outputs. So one straightforward way is to aggregate token embeddings towards cell level or column level. And then, but if you want to fine tune it, I think there are many interesting approaches to that. I want to zoom in on tapas, which is a model for question answering. And there, what they do is they predict the aggregation operator. So for example, sum or average. While also a second pre-training or fine-tuning task is cell selection, where they predict the span of cells that are relevant to actually answer the question. So, okay, what does that look like? Here is an example. So you have this table here about actors, and we have a few questions. So how old is Leonardo DiCaprio? Okay, you get a prediction of the average aggregation operator versus 45. This is one value, so the average, that's still valid. So that works great. If you ask a question that is more complicated, what's the sum of the number of movies, you still get a very good result, actually. So you get the predicting sum of this span of cells, so all 3 cells here of the entire column, and you get actually the accurate result. So that's perfect. But you have to be really explicit. So if you have a slightly more ambiguous phrasing of the same question, you might end up with a very different and wrong number. So although you can do many interesting tasks, for example, for question answering over tables with such models, there are still many challenges when it comes to more complex tables or perhaps more complex questions or complex queries. So I think we touched upon this topic a little bit, and I think especially for tables and these models, the big challenge is to actually generalize out of domain. So, and I think that's unlike with natural language, for example, where you see that word embeddings generalize pretty well across different domains. But here you see a table of a simple task, so column type prediction. So given a certain table, what are these columns actually about? And what you find here is tabular, which is actually one of the early pre-trained models. It fails miserably on a data set that is completely out of domain. So it actually fails to F1 score of 0.14. And I think that just illustrates that we need really representative data, especially when we want to learn representations of tables. What is also interesting to note about this table here is that, for example, Chorus, which is actually a GPT-based approach to the same task. So you might think like, okay, I just dump my table in ChatGPT and I ask it for the column types in this table, but actually it doesn't outperform the baseline. And this baseline is actually a model that I built in 2019, and it's just a featureized deep learning based model. And it outperforms GPT with quite some margin. And this is not my paper, so they really tried hard to actually beat this baseline. So what are the challenges? So I think it really comes down actually to the data. And when it comes to tables, it's really hard to get that data. And it's not that in your databases, we typically find tables that you can find on HTML web pages, right? So these tables look really, really different. So you can find very messy data. Tables can be extremely large. You can have like full databases with lots of tables that all relate to each other. You can find non-descriptive headers, numeric data, and so on. So many interesting challenges that transformers nowadays don't really tackle well yet. So what data do we actually have and what data do we actually need? Well, I've done some research on this during my PhD, and all the corpora that exist are web-derived data sets. And well, as said, web tables don't resemble database tables well. So what data can we actually use to also serve offline data analytics pipelines, for example? Well, here we resort to GitHub as a data source. So I went to GitHub, I searched for CSV files with the term ID, which is one of the most common attributes in databases. And I found close to 60 million CSV files only for this query, which really illustrates the huge scale of GitHub for finding such data sets. So that's excellent. And we built a data set out of it. Pretty straightforward. We just take all the CSV files, we parse them to tables and enrich these tables with column level metadata. So what do we actually have? Well, GitHub makes it extremely difficult to crawl data from it and extract data. So we now have 1 million tables, which is just a starting point. And we also publish the underlying 800,000 CSV files, which are really gold for example, CSV parsing use cases as well. And we find that these tables much better resemble database tables as we find in typical enterprises and organizations. And we also show several use cases with this data set. So for example, column type detection, for example, to standardize data models, but also schema completion. So given a few attributes, what are relevant attributes to add? And this can be interesting also for data science pipelines, where you might want to integrate different tables together. Okay, so then the most recent work, I think we have a data set that we can use to generalize these models towards. But one thing that was also missing is really understanding whether these table-focused or table-tailored transformer models actually capture the key properties of tables well. So with Observatory, we introduced a framework that kind of recalls and recaps all the properties of tables. And you might remember this perhaps from a database course, but Edgar Cott has introduced a relational model years ago. And there he, for example, introduced a few principles. One of those principles is that the order of the rows is insignificant in a table. However, we find, as we see in a bit, that many of the models actually are very sensitive to the order of these rows, which is really impacting downstream applications. So that's an example of a property that we define. We have, I think, 8 properties of relational tables, and we collect them and assess existing table models with respect to these properties. So yeah, as I said, only few models are not sensitive to the row and column order, as you can see here. So for example, Turl, which implemented this visibility matrix, we found that is actually extremely sensitive to the order of the rows in this table. But what I think is also interesting is functional dependencies, which are really useful for databases as constraints. But these are very poorly reflected, if not at all, in the embeddings of these tables. So there's really a lot of work to do. And we had some other findings there as well, and the other properties, of course. But yeah, just to illustrate the impact of such principles, to kind of reflect such principles in these embeddings, we find that only by shuffling a few rows in a table already changed the column type predictions in 34% of the tables, which is really has a lot of impact in downstream applications then. So yeah, with the many open challenges, I think we came across a few of them already, but I think with the right data that we now have and the analysis that makes us understand these models much better, we are now able to actually design better architectures to deal with the heterogeneity of the data, but also with the structure that tables come with, along with the dimensions, of course. So I think one downside is that LLMs have this input limit constraint, and of course tables can be so large that won't fit into it. So that's a huge challenge. Of course, we talked about generalization, beyond these toy tables and SQL queries that I just showed. But other challenges are that we need to handle lots of sensitive data. So tables typically live in enterprise databases. So we need to really accustom to that kind of company setting as well. Now, we've just talked about like embeddings of singular tables, but of course we need to also move towards embedding of full databases. And to that end, I think if we reach that stage, we can actually explore many more applications across the entire data management and data analytics pipelines. So a few key takeaways that I hope you bring with you. First, tables really actually dominate the data landscape, especially in enterprises. but also in government organizations, for example, particularly for analytics use cases. So we really need to train and tune also the models that we have on representative data that we find there out in the real world. Yeah, I'm here to say also that tables aren't just natural language. There are many particular aspects of tables that we should take into account. And we only scratch the surface, really, when it comes to the architectures and applications that operate on these tables. So there's much more to address and, well, much more to explore yet. So I'm extremely excited about it. If you have thoughts on it, please feel free to reach out. We also organize a workshop on this at NeurIPS this year that I hope you might be interested to join. With that, I want to thank you.
Excellent talk. Thanks very much. Any questions from the audience here? Yes.
Yes, thanks for the very interesting talk. So in principle, there are two approaches. The one is like what you presented with embeddings. The other approach is like SQL generation and then send it to your database. What do you say is the fundamental advantage of representing embedding approaches, which you can't do with like, yeah, you take the schema, generate an SQL query, and run it with your database. So what's new and novel? What's working? Well, could be working with embeddings if we get it right.
Yeah, I think that's an interesting question. So I think you're referring to the huge like takeoff of text to SQL. There I want to note that many of these approaches also take into the semantics of these tables. So one way or another, they still leverage these semantics. And I think it's just, you also need that. So you need to know what's inside a table and what the kind of like general representation is to make sense of, for example, a SQL query where the variable names can be very specific. But if you have like many tables and many queries, then you can much better generalize in that sense. Not sure if that answers your question really, but to some extent, right? Yeah. Yeah.
You're a fan of text to SQL or?
Well, actually, I would be. I'm not a big fan of text to SQL yet. Not really my area, but I would like to move towards table to SQL. So just, because that kind of assumes that you have a certain question and then translate it to a query. But I think we can really leverage all the tables much better if we generate interesting queries from a table itself instead of relying on people that have to explain what is interesting to ask on a certain table. So I think there's a lot of potential in table to SQL instead of text to SQL, but of course they go hand in hand and complement each other very well.
Thanks for the great talk. I remember that TabNet was one of the first works, or was popular was in the beginning, applying transformers to tabular data, but you didn't mention it. So is it not relevant anymore, or?
I think TabNet is for tabular machine learning. Is it?
I mean, it's the first work they apply transformers for tabular. I don't know exactly what evaluation was. Maybe
So I think that's an interesting kind of two streams that come together. So I've been talking about, for example, tabular, which I think it was the first pre-trained model for tables. And then TabNet, I think, targets machine learning use cases. So tabular machine learning, back in the days, that's like I have one table and then I apply a model. I train a machine learning model on it and then predict the outcome on row level, let's say. And here we try to learn semantics of tables across many like millions of tables instead to find general patterns. And I think TabNet, but I don't remember it that well, was targeting tabular ML, so data science use cases.
All right, thank you.
And I think actually, just to add a little bit, I think there might be very much potential also for data science and tabular ML if you learn, for example, data science pipelines jointly with the tables that they operate on, so that you can predict, for example, interesting pipelines for a given type table as well.
Hi, thank you. It was very interesting and very sort of large in scope with the different avenues. I was wondering about, you mentioned it briefly at the end, it's one of the challenges, which is the sensitivity and privacy aspect. You also mentioned this sort of need for data and how you sort of made this bigger data set because it was very needed. So how do these two, what are the specific challenges in designing these data sets, and how do these privacy aspects, like they obviously the most sort of sensitive data will not be in public data sets. So how are these two things sort of challenging each other?
Yeah, that's a good question. I think what is problematic is that companies just keep their data private. They don't share that at all, and they also don't want to have that data leak into models. So there's like a legal kind of problem on that side. But because companies, so tables typically reside in data warehouses, databases, and therefore you cannot really find them easily on the web. So it's very hard to build a extremely large scale data set that is representative for all the domains out there, just because no one really shares or publishes their data. You have some open data portals, but they are still relatively small scale.